You can see, yes. So you can see this schematic spectra, that a line in the Mossbauer spectrum has been shifted towards the positive side of the recoiling velocity x-axis. You can see this is the delta. What do you mean by the delta? Shift in the line. And what causes this shift? Those factors we discussed in our previous class. The first one being the unequal sizes of the nucleus in the excited and the ground state. And the second main important factor is the electron density at the nucleus. And we saw that if the electron density at the nucleus increases, that results in isomer shift. And what are the factors which increase the electron density? First of all, the occupancy of the s orbital electrons. And this is how the energies of the nucleus, which are showing isomer shift, can be represented. This is without isomer shift. The relative position is 0 mm per sec. You see, because of the isomer shift, could be of either of the reasons, either because of the radius difference or because of the electron density experienced by the nucleus, or because of the combination of both the factors. You see, the energy levels have shifted their energies. And even we know that the I value for the nucleus in the ground and the excited state would be different. This is not seen in NMR example, is it not? Because in NMR we are concerned with only one nucleus. Here we are concerned with two nucleus, one in the ground state and one in the excited state. When I said two nucleus, it is not two nucleus of two different elements. Two different nucleus of the same element for the same isotope in the ground state one and in the excited state. So what does it tell when the I values are all different? So in the excited state, the nuclear structure and its properties are entirely different than that of the ground state. The size can vary, the spin quantum number can vary, spin angular momentum can vary. So almost they behave as independent nuclei in the ground and the excited state. But because of isomer shift, the energy levels have shifted their positions. See this. And in any spectroscopy, when you are representing energy levels, what does a double line like this tell you? You can see this in a number of cases. In fact, even in Banwell textbook, many energy levels are marked with this double cross lines. So what does this mean in any spectroscopy? In any energy level diagram, basically. When you have a double cross line like this, what does it mean? Any answer? What does it mean? Okay, it simply means the delta E is too large. Okay, is so large that it cannot be depicted to scale. It cannot be represented to scale. So in such cases, a double cross line is always used. And you know, delta is in fact too large. It comes in the region of gamma rays, 10 to the power of 18 hertz. And that is why usually a double cross line is put like this. Anyways, so if there was a absorbance relating to this transition, we would have got here on this line. Since it is shifted to a greater side of delta E, we are getting a positive, this is called positive isomer shift tilt. What causes positive and isomer shift? That depends on the previous formula we saw. Whether the radius ratio is radius ratio is below 1 or above 1, these factors. Anyways, now we will move on to one more factor which influences the spectrum, Mossbauer spectrum. That is the nuclear quadrupole interactions. What do we mean by nuclear quadrupole interactions? First of all, okay, what do we mean by nuclear quadrupole? In fact, we have an entire unit dedicated on NQR spectroscopy, which I'm going to take up after Mossbauer. So the details of all those nuclear quadrupole movement we are going to see, and how a spectroscopy originates because of these things, we are going to see in detail in our next discussion. But as of now, you just have to understand this much, that the charge distribution of the nucleus can be represented using ellipsoids. Of course, these are not actual pictures of nucleus, never. These are the pictures of the ellipsoid drawn for the charge distribution of the nucleus. Okay, fine. So, we do like this in quantum mechanics a lot of times. Gradient of something or a mapping is used to understand the distribution of something or gradient. We use maps, three-dimensional maps called ellipsoids, and there are mathematical processes, protocols for drawing these ellipsoids. Anyway, we are not going to those things. We just are using the results of those calculations. The ellipsoids are like this. You can see that the ellipsoids can be of three basic shapes. What are these ellipsoids? These are the ellipsoids for the charge distribution of the nucleus. And first of all, what is a nucleus after all? It is simply a collection of charges, protons, positive charges, right? What is the charge of the nucleus? Positive. And that positive is not because of a single positively charged particle. It is because of a collection of numerous protons inside the nucleus. So when all the protons are coming together and forming nucleus, how, charge is also directional. So when you account for this directionality of the charges, you can construct an ellipsoid representing the charge distribution. The shapes can be either spherical or oblate or prolate. In fact, I'm sorry, this is the spherical shape, this is the oblate, and this is the prolate shape. Fine. So when there is a spherical distribution of charges, then we tell there is no nuclear quadrupole movement. The nuclear quadrupole movement doesn't exist for spherical nucleus, basically. I shouldn't say spherical nucleus. If the charge distribution of the nucleus is spherical ellipsoid, giving you a spherical ellipsoid, then we call there is no nuclear quadrupole movement. But all nucleus are not like this. There are many nucleus which deviate from the spherical shapes of the ellipsoids, particularly the ones which have the spin angular momentum, not spin angular momentum, the angular momentum, I value is greater than half. So those nucleus assume a non-spherical charge distribution, greater than half. Please note the difference here. It's not in our usual discussion, I value is 0, they are inactive in so many spectroscopies. I value is half, it is still spherical. I value is more than half, can be 3/2, 5/2, 1, whatever. Then the ellipsoid becomes non-spherical. So when the ellipsoid becomes non-spherical, so what happens? The asymmetry in the electric field comes into picture. Fine. So now this asymmetry in the electric field creates something called electric field gradient. Right? So this is called simply EFG. EFG term we are going to use repeatedly in our nuclear quadrupole moments NQS spectroscopy later. But as of now, what is creating a gradient? The unsymmetrical distribution of the charge, asymmetrical distribution of the charge is creating an asymmetrical electric field. After all, what do you mean by a gradient? Gradient means there is some inequality. That is called a gradient. So EFG is created. Now, this EFG, existence of an EFG in the nucleus alters the nuclear energy level. It's fine. But how does it alter? We are going to see now. You see, those are only like a three-dimensional representation. Actually, these are the ellipsoids which I was talking about. For an oblate nucleus, the ellipsoid is like this. For a prolate nucleus, the ellipsoid is the other way. I mean, the prolate nucleus are also called cigar-shaped nucleus. Cigar is a cigarette, basically. So a small cigarette-shaped, a prolate nucleus is. So cigar-shaped nucleus. Now what happens? Fine. Now what happens if, let us take an isotope with I is equal to 3 by 2. And the two common isotopes of the Mossbauer we study, iron 57 and tin 119, both are having EFG in them. Why? Because they are of not spherical ellipsoids. These nucleus are, instead they are prolate shape, the cigar shaped nucleus these are. And if I is equal to 3 by 2, what are the possible values of Mi? If I is equal to 3 by 2, what are the possible values of Mi? 3 by 2 plus 3 by 2 plus half minus 3 by 2. These are the Mi values. Now, the Mi values, okay. When are you going to have a split in the Mi values? Basically, when in the ESR spectrum, even whatever we have seen, the S is equal to half, particularly the hyperfine interactions, is going to get split into plus half and minus half. If S is equal to 1, it gets split into minus 1, 0, plus 1. And what are those minus 1, 0, plus 1? Those are all MS values. When splitting happens? In presence of some field, right? And if the splitting is with the atomic orbitals electrons, then this is called Siemens effect. The splitting is. So whether Siemens effect is coming into picture or whatever, if there is a field, basically, if those particles, example electrons or nucleus, are experiencing an external field or internal field, then there is going to be split in the degeneracy of spin states. And when they are split, you are going to see the energy levels, delta E, all those things coming into picture. Similar thing happens. And whatever the electric field I am talking of is not external, it is internal. That is the field which is created because of EFG, nuclear quadrupole moment. Doesn't exist in all nucleus. Only nucleus with I is equal to more than half. Fine. And that is the basic property of the nucleus. I mean, we can't tell why it is existing like that. It's the way it is existing. Simple. We can only explain the structure of it, not the reason. Of course, you can even explain the reason. You know, like we have many theories to explain the electronic structures. To explain the nuclear structure also, there are theories which we don't study in chemistry, basically. Maybe the physics people do that. There is something called shell model for the nuclear structure. And using those shell models, you can predict the charge distribution, the ellipsoids, the shape of the nucleus, all those things. And particularly those who are interested in the radioactivity of the I mean, what is that field called as? The radiology. So they study this nuclear structure in detail. Anyways, so now what happens because of that splitting? You see what has happened? There is a ground state nucleus and there is an excited state nucleus. The ground state nucleus has I is equal to half. That means what? It doesn't show nuclear quadrupole moment. The ground state, example iron, let us take it as iron 57. The ground state iron 57 doesn't experience nuclear quadrupole moment. It may experience some other factors like isomer shift. Therefore, the energy can slightly be raised or lowered. But however, the excited state Fe, see that excited state Fe, and Fe is prolate type nucleus having a nuclear quadrupole moment and EFG. Therefore, the I is equal to 3 by 2. Actually, I is equal to 3 by 2 has many degenerate spin states in it. Because of the application of the field, you have split the degeneracy. And if the degeneracy splitting is full, that means every spin state will be of different energy, like plus 3 by 2, minus 3 by 2, plus half, minus half. But in the interaction of the EFG, what happens, which I'm going to show you in this picture. I mean, of course, I'm sorry that this picture is not that bright. Maybe it's difficult to even make out the drawing. Anyways, because I've just taken a snap of your Banwell spectra given in your Banwell. I mean, the energy level diagram given in your Banwell book. Anyways, with a lot of difficulty, we'll understand this, no problem. You see this? This is the cigar-shaped nucleus we are talking of. And whatever the case, the MI values, MS values, what are those? Those are all the orientations of the spin with respect to an external electric or a magnetic field, right? So the nuclei also orients in these 4 different ways, corresponding to plus 3 by 2, plus half, minus 3 by 2, sorry, minus half, minus 3 by 2. But here, why don't they get split into 4 energy levels? Why are they splitting into 2 energy levels? And each energy level is doubly degenerate. Plus 3 by 2, minus 3 by 2 will be degenerate. Plus half and minus half will be degenerate. So splitting is only twofold. It gives only a doublet. Why? Why? Because, I mean, there is no requirement to understand in very much detail. The simple reason is this. The angle formed with this nucleus with an external electric field, not external, with an electric field, maybe internal electric field, theta, example, is having the same value in both these orientation, plus 3 by 2 and minus 3 by 2. Therefore, the interaction, extent of interaction is identical for both plus 3 by 2 and minus 3 by 2. They are raised in energy to the same extent. The same argument holds good for plus half and minus half, but they are lowered in energy, and both plus half and minus half are degenerate. Anyways, but this is for prolate shape. For the oblate shape, how is the splitting? Same, except that plus 3 by 2 and minus 3 by 2 will be the lower energy levels, whereas plus and minus half will be the higher energy levels. Otherwise, same. Now the delta E here, is the energy of interaction due to the electric field gradient, EFG. So basically, if you can measure this delta E, you are in turn measuring the EFG's magnitude. So you see this? This is what I was talking about. So the delta between those split energy levels is nothing but the value of EFG. The calculation of EFG is important in NQR. You can do it in Mossbauer also. So E, in what are these terms we are going to see later when we take up NQR. So you can calculate EFG. So now what happens? If there was no EFG, there was no interaction, there would have been only one line in the spectrum. Even because of isomer shift, there is still one line. Isomer shift doesn't cause splitting. It only causes displacement in the position of the line. Whereas because of splitting due to EFG, you see there are 3 energy levels, and the transitions can be from example 1, 2, 3. If there are, these are labeled as 1, 2, 3, transitions can be from between 1 and 2 and 1 and 3. So you are going to observe 2 lines. And what is the difference between these 2 lines? Is the difference between the split energy levels in the excited state, that is the EFG extent. So this is how you can represent the energy levels after splitting due to quadrupole interaction. Now you see, I've just taken you one complicated example a bit, wherein the ground state I value is 7 by 2, whereas excited state I value is 5 by 2. So here the picture becomes more complicated. Why? Ground and excited both experience quadrupole splitting, whereas in the previous case of iron, only the upper state, the excited state, was experiencing quadrupole splitting. Now you split this 7 by 2, you get plus or minus 7 by 2, plus or minus 5 by 2, plus or minus 3 by 2, plus or minus half. So 1, 2, 3, 4. Essentially, you get 4 energy levels. And what about 5 by 2? Plus or minus 5 by 2, plus or minus 3 by 2, plus or minus half. So you get 3 energy levels. Now, once you write all possible energy levels, of course, every energy level is a doublet here. I mean, is doubly degenerate. Please don't forget that. Plus or minus 7 by 2, plus or minus 5 by 2, plus or minus 3 by 2. So they are doubly degenerate, each energy level is. So totally, how many transitions are possible for a nucleus with the ground state I is equal to 7 by 2 and excited state I is equal to 5 by 2? 1, 2, 3, 4, 5, 6, 7, 8 transitions are possible. So now you see all transitions are starting from the ground energy level itself, ground nuclear energy level itself. But there is a restriction of all number of transitions that is given by the selection rule, basically, right? So what is the selection rule for Mossbauer spectrum? So delta mi can be 0 or delta mi can be plus or minus 1. So 0 means what? From plus half, minus half, it can go to plus half, minus half. Or from plus half, minus half, it can go to 3 by 2 also. So you see, so these are all the transitions. See this. This is a transition 7 by 2, 5 by 2. So where delta mi is equal to minus 1. Apply the selection rules and write down all possible transitions. So you should get a spectra which is having 8 lines in it. Anyways, but in Mossbauer we are more interested in this iron and tin. Therefore, you get only 2 lines in iron. Anyways, now look at this picture. You see this? Look at this picture. This is simply the nucleus which are not experiencing any perturbation, any disturbance. Therefore, this would give to a hypothetical line at V is equal to 0. But once it experiences isomer shift, the line is getting displaced a bit towards positive side. And now this is a shift. This is a spectra with combined effect, the isomer shift effect as well as nuclear quadrupole splitting effect. Because of isomer shift, you get a line here which is split again because of nuclear quadrupole interaction. So it is split into 2 lines. So show 2 lines in the spectrum. 2 transitions corresponding to 2 lines. You see 1 line here and 1 line here. Now, of course, the gap between these 2 lines will be the gap between the split energy levels of the excited state. So you can even write energy level like this, showing many factors in the same energy level. In this energy level diagram, 2 factors are shown. One is the isomer shift, the quadrupole splitting effect. So because of nuclear quadrupole splitting, what are the informations we can get? This is very important. Now starts our chemical analysis part. What are the informations we can get? We can, first information is we can get the information whether the nucleus has a EFG in it, electric field gradient in it. That's the first information. If there is electric field gradient, definitely you will get more number of lines in the spectrum because of the splitting in the energy levels. And what is the extent of EFG? Its value can also be calculated by using the Mossbauer spectra delta I obtained from Mossbauer spectra. And also application of magnetic field gives more information. Next class we are going to study that. This is now the last point. What is that? I mean, you please send your names in your chat box. Yeah, I have only 10 minutes. Now I will show you one spectrum. Yes, fine. Of course, this is again a snapshot from the Banwell book. See this. This is the spectra of potassium ferrocyanide, K for FeCN6, potassium ferrocyanide. Anyway, the complex ion, what is the other counter ion is not important. Iron is important because iron is Mossbauer active nucleus. It is giving you a single line. But the nitroprusside. So what is nitroprusside ion? In the ferricyanide or ferrocyanide, you have to replace one CN with NO. Then this become nitroprusside. The spectra of nitroprusside is having two lines in it. And these two lines are like matching the quadrupole splitting pattern. Is it not? The same thing what I showed here. It is matching the quadrupole splitting pattern. So what does it mean now? The FeCN6 is not experiencing a quadrupole splitting, whereas nitroprusside ion is experiencing a quadrupole splitting. But this brings us to a contradiction now. What were we talking of till now? The nuclear quadrupole splitting is due to the shape of the nuclei. I mean, the ellipsoid, shape of the charge distribution ellipsoids. Now, whether the iron nucleus will have the prolate shape, whether in FeCN6 complex or nitroprusside complex, the shape of the iron nucleus should not change, right, in the complexes. Then why there is no quadrupole splitting in one case and there is quadrupole splitting in the other case? Okay, the answer I'm going to give now, it's very important. The answer is, even though an electric field gradient exists because of the shape of the ellipsoids, or shape of, simply let us call it shape of nucleus, even though EFG exists, for the EFG for the energy, nuclear energy levels to get split, this electric field gradient should be in an asymmetrical field. Okay. So what do you mean by this? So whatever the, yes, see, I've shown a field here, right? What is this field? It's an electric field or magnetic field, either external or internal. Nuclear quadrupole splitting, we are talking about internal field. Now the second field is existing. Electric field gradient is existing because of the nuclear shape. That is default. It is always existing, irrespective of what are the other atoms on the iron. Always existing. But to split it, but to split the energy levels, the field, the second field what we are talking about should also be asymmetric. This is one more important. Now, what happens in our FeCN6 complex? In our FeCN6 complex, what is the symmetry of the crystal field? What is the symmetry of the crystal field in FeCN6 complex? Octahedral. And this octahedral has a spherical symmetry, right? In terms of the field, crystal field. Therefore, although EFG is existing in Fe nucleus of FeCN6, but the field, crystal field, the external field, what we are talking about, the second field interacting with our EFG is spherical. Therefore, there is no quadrupole splitting. But once you replace your CN minus, at least one CN minus with one more ligand, like in sodium nitroprusside, we have replaced with NO ligand, the spherical field becomes asymmetric. In now case, the interacting field is asymmetric and there is an electric field gradient also. So because of these two interactions, you are going to get a split energies in the excited state of the iron. Therefore, you are going to see lines due to quadrupole splitting. Do you understand? Okay. So that is how we have to answer this question. Although both these complexes has iron in it, why FeCN6 is not showing that nuclear quadrupole splitting, but Fe nitroprusside is showing it. See, the nuclear quadrupole moment exists for both nucleus, both iron in both complexes. There is no doubt. Electric field gradient also exists in both the cases, but this electric field gradient doesn't interact with the asymmetric field. It interacts with a symmetric field in case of FeCN6, whereas it interacts with an asymmetric field in case of nitroprusside. That is why the splitting happens. So this is regarding the nuclear quadrupole splitting and its applications. So looking at the Mossbauer spectrum, what are the information still now we are obtaining? Because of isomer shift, we can obtain information on the oxidation state of the metal ion, the electron density around the nucleus. Because of isomer shift, we can obtain that information, as well as the information on the radius of the excited and the ground state. Because of nuclear quadrupole splitting, what is the extra information we are obtaining? We are obtaining information about the geometry of the complexes, whether it is in octahedral or a disordered octahedral, or the octahedral symmetry is destroyed, tetrahedral, whatever. All these effects manifest in terms of split lines in the spectrum. In this way, Mossbauer is helpful, very helpful technique, at least in cases like iron and tin. Very accurate, fast, reliable method for characterization of iron compounds and tin compounds. Organo-tin compounds. There is a class of compounds called organo-tin compounds, which you study in your organometallic chemistry. So Mossbauer spectra can be well applied to such cases, organo-tin compounds, to study their bondings and all, and their chemistries. Fine. So I'll just stop now here. We will